Welcome to the second part of the problem-solving session for Chapter 5. We pick up in question 8, which states a man weighs 900 newtons on the Earth. The question is, what is his mass in kilograms, and what would he weigh on the planet Jupiter, where the acceleration of gravity is 25.9 meters per second squared? So let's begin. We are given his weight on the planet Earth. In other words, F sub g is given by his mass times the acceleration of gravity on the Earth, and that is 900 newtons. So his mass is then given by his weight on the Earth divided by the acceleration of gravity on the Earth, and this gives us a value of 91.8 kilograms. Once we obtain his mass, now we can determine his weight on the planet Jupiter, since F sub g, the force of gravity on the planet Jupiter, will be equal to his mass times g for the planet Jupiter, and that will be given by 91.8 kilograms, the mass we just determined, multiplied by 25.9 meters per second squared, the acceleration of gravity on Jupiter. This gives us a value of 2,380 newtons. So this is what he would weigh if he could stand on the surface of the planet Jupiter, which of course he can't because Jupiter is a gaseous planet. Okay, question 9. A fish has a true weight of 40 newtons and is hanging from a spring scale in a moving elevator. What is the apparent weight of the fish in each of the following situations? Okay, the elevator accelerates upward, 2 meters per second squared. The elevator accelerates downward at 2 meters per second squared. The elevator moves at constant velocity, 5 meters per second. And the elevator cable is broken so that the fish, as well as the elevator, are in a state of free fall. Well, let's see. We have a free body diagram that has been drawn for us. So let's go ahead and just repeat it here. We've got the fish. We've got the force of gravity pulling on the fish. And then we have the support from the spring scale, which we will just label the normal force. It could be the tension. For us, the normal force will be the apparent weight. So once we solve for the normal force, we're solving for the apparent weight of the fish. Okay. Well, we know that there will be no forces acting along the horizontal. A sub x is equal to 0. And all or any of the accelerations that the fish will experience will be along the y direction, and these are given to us in the different parts. Well, let's go ahead and write down Newton's second law along the vertical, and you can see that we've got the normal force, which will be the apparent weight, minus mg equals ma sub y. And let's go ahead and just solve that for n, mg plus ma sub y. And let's use this expression to determine the normal force in each of the cases that has been given to us with the different values of a sub y. One other thing that we better have, and that is the value of m for the fish. Now, they told us that mg is equal to 40 newtons, so of course that will be the number that we put in here. But let's go ahead and determine m, since we will need it for the next term. That's 40 newtons divided by 9.8 meters per second squared, and that is given as 4.08 kilograms. That will be the mass that we will insert here. Okay, so in the first case, we're told A sub y is equal to positive 2 meters per second squared. So we can see that N is equal to 40 newtons plus 4.08 kilograms times positive 2 meters per second squared. In this case, we get N equal to 48.2 newtons. So in the case where the elevator is accelerating at positive 2 meters per second squared, the apparent weight of the fish will be 48.2 meters. Okay, let's go with the next situation. In this case, the elevator is accelerating downward at 2 meters per second squared. In this case, you can see N equals 40 newtons plus 4.08 kilograms times negative 2 meters per second squared. That gives us a value of 31.8 newtons. So this is what the fish appears to weigh when the elevator is accelerating downward. All right, how about when the elevator is moving at constant velocity? We don't care what that value is. The fact is that if it's constant velocity, the elevator is not accelerating, and therefore 4.08 kilograms times 0 gives us an apparent weight of 40 newtons. In other words, the apparent weight of the fish in this case is equal to its true weight. Lastly, A sub y equals minus g. In this case here, the cable is broken, and so you can see that N will be equal to 40 newtons plus 4.08 kilograms times negative 9.8 meters per second squared, giving us an apparent weight of 0. So in fact, what happens is that the fish is falling at the same rate as the elevator and the hook, and therefore appears to be in a state of weightlessness. Now that doesn't mean that the fish has no weight, it's just that there is no support against that of the force of gravity, and so the fish will be falling at the same rate as the elevator and the hook. In fact, this is the case with the astronauts aboard the space shuttle. Since the space shuttle and the astronauts are all accelerating at the same value as the spaceship orbits the Earth, there is no support provided by the shuttle. This concludes the second part of the lecture problems in Chapter 5. See you next time.